Hello again, welcome to this new class. This class will be about meshing. So, after having our geometric model, we will need to perform a conversion step, which is obtaining our finite element. In finite element analysis, we divide our model, our geometric model or physical model, into final pieces, our finite elements, and those elements are all connected between points, characteristic points, which are the nodes. These points are lying on their boundary, on their circumference. This connection is a set of equations called shape functions. That's explained in the FEM theory. Each finite element has its own set of shape functions interconnecting all the nodes of the element. Of course, you will have more elements which are adjacent, and they will share the common nodes for each edge. Can be linear elements, 2D or 3D elements. It can be a surface element or a solid element. And the shape functions of all elements in the model will be tied due to the common nodes. To build the mesh in CivilFEM, we must take these steps. First, we must select the appropriate structural element. We'll see which are the available structural elements, which will cover all type of behavior. Then set the mesh control for each structural element, which is the size and the method. Then obtain the mesh, and after meshing, we can usually correct the mesh size, setting it a finer or a coarser mesh, because all of this is very related to the accuracy of our results. Okay, usually in the beginning will be a hit and miss procedure, because in the beginning we don't know if we have a big or small error in our results, so we have to always take some time setting the correct mesh size, and even if we want elements of higher order, we'll see that later. Elements of higher order will have more nodes, it has more accuracy, of course, but we have to always estimate cost time, number of nodes versus time consuming of our calculations. If we open the software, we will I see some examples of meshing. We'll start with a simple example, just beams. We'll create some linear elements. So we start with just simple geometry, line. So we see how to mesh line, but here we have our line. We create our material, a cross section, and here we have our structural elements. Okay, if I go back to my presentation, what are the structural elements in CivilFEM? A structural element is a kind of group of finite elements of the same type with the same behavior. We have these 5 types of structural elements: beam, truss, shell, solid, and cable structural element. We have our physical model, which is a kind of table. It's composed of slab, a horizontal slab, and 4 columns. We have 5 structural elements. One is the shell structural element, which is the slab, and the other 4 are the beam structural elements, which are the columns. Each structural element will be meshed, and we will obtain finite element. For the case of the slab, once we mesh, we obtain our finite element model of elements and nodes. If we select as mesh control 4 node shells, the shell structural element, we will obtain 32 finite elements. In this case, we set just 4 elements in this direction and 8 in the other direction. And for columns, we set number of elements of 7. We have 7 finite beam elements for each column structural element. This is how we perform mesh in CivilFEM. First, selecting our structural element. We have linear elements, structural elements, which are beam, truss, and cables. These are linear elements because one of the dimensions, which is the length of this structural element, it's much bigger than the other two, which is the dimensions of its transverse cross section. We will always recommend to use beams because computational cost is very low. You can obtain very accurate results using beams. Usually, if you want to perform a code checking, mostly linear structure, but a linear structural analysis, a global analysis, it's very accurate to use beams. If you want to change your section and maybe one dimension, that's very easy and fast. The beam structural elements have bending stiffness. If you want to take into account the bending stiffness, beams are the best option. But if you only want to work with anaxial elements, you have trusses. And in the particular case that these axial elements only work under tension, then nonlinear cable structural element is your choice. So we go back to the software, and for this case I will select a beam structural element. What do we need for the definition of a structural element? We will need a cross section which already has its material assigned and a geometry. Okay, we have only one geometry, so we select our geometry, and then we have here our different options, properties for the structural element. We can always change the cross-section type. We have seen that it can be constant or tapered, or use different zones for the rebar definition. We can set different orientation, and we'll see later that we can set an offset to the load application. Okay, by definition, the loads are applied to the gravity center of each element. And we can define as well hinges in different axes. If we want to, there are different options to define a hinge, but one is for each end of any structural element, but we can define for each internal node connections, we can release or couple degrees of freedom and create rigid areas as well. It has a coordinate system. Each structural element, by default, the element's axis will be oriented with respect of the global Cartesian. If we are going to perform a code or standard checking, we will need some data which are not related to the structural analysis, but we will need them for the post-processing of the code checking specifications. In this case, as we have by default the Eurocode 3, we have some parameters that are related in this case for the backlink checking, the effective lengths, the coefficients for moments, okay, area holes that will be needed for some of the check results. And important, what we are going to see now is the mesh controls. What do we have here? By default, the type of the mesh for linear elements will be uniform. We can try with this. We can set a name always. It's important to save your model, as we don't have an undo option unless, well, you're using the script editor. Here we have our beam. You can see that we have 10 elements. Of course, if we change our cross section, in case we want to set an angular shape in this case, if we want to change our section, it will be automatically updated. Okay, but I want to show you that this was the default mesh. We can change the orientation, but I want to explain you the other options for meshing beams. The control can be, in this case, by length or by number. I set 10 elements, but I can, if I want to set a particular size, I can set here half a meter for each element. And we can see now that we have now 20 elements. Here in the mesh info, always you have in the output as well, you will have the information, the number of elements, if you want to control them. Okay, and we have another options as well. Instead of uniform, can be variable. This is very useful if we want to perform an error estimation. If we found that we have to refine our mesh, sometimes it's not needed for all of our model. So we have just to refine particular areas of our model. This can be done with linear elements, shell elements, or solid elements. Okay, so this is very useful in this case for beams, that we have this option. Okay, that can be our mesh finer in just one end of our structural element. In this case, the control can be the same by length or by number, which will be the number of elements, and the relation, the ratio between the first element and the last one. So if we set 5 elements and a ratio of 2, a relation of 2, the last element, as you can see, is double than the first one, and then the transition is done automatically by the software. If we want the first one to be much bigger than the last one, we just change the ratio here of half. The first element will be double than the last one. Another option is to, instead of having a linear variation from one side, is just to have it from the center. So different size will be a quarter of the elements which are at both ends. And each beam structural element will have 2 ends, Y and Z. Here we can set the hinges for each, and we can click here. Depending on which axis are the hinges are performed, we will see different view options. So these are the options for beams. For the 3D or 2D case, the slab has one dimension, which is the thickness, much smaller than the other 2 dimensions. The shell structural element will be your choice, which matches with accuracy the behavior of your structure. Okay, here a beam, it doesn't fit to the behavior of this structure. So we start now meshing areas, surfaces, using
shell structural elements.
And we want to create, for example, another quadrilateral. Okay, and now we want to perform a mesh of this quadrilateral, and we will use the same material, the steel material, and now we want to set first the thickness. We select the geometry, and here we have it. Now we have our shell, and we have our different options here. Okay, we have different controls. The first one is usually the most common control, which covers all 90% of the typical mesh for shell elements. So usually you will leave this control as default. And here we have two options: triangles or quadrilaterals. First, we can check with triangle. We set 1 meter. Here you can see the different options that we can select different elements, so we can see the definition of each element, and as well select nodes if you want. Okay, by default we have our structural element here. So what are the other options that we have for meshing shells? We use the triangle, but we can use quadrangles. We have always to clear the mesh before starting a new mesh. Now we have quadrilaterals, most of finite elements, but we can, if we want to, well, set more customized controls in our mesh. We have these meshing controls, which are local controls. We can use one in case we want to, in this particular edge, we want to set another or the same as length or number. We can set here regardless the global mesh size of the element. We can set here our local mesh controls. Just click on, and we see here the result. Okay, we can do it with triangles as well. And here we have it. Here we can see with triangles better that we have a particular local control here, and rest of the elements will have 1 meter of size. So what do we have to do if we have different structural elements? We had meshed a shell and a beam, but we have done it independently. We have different buttons to mesh. We have this global one. It's the color of its orange one. This mesh will mesh all the model. Okay, and this will clear the mesh of all structural elements. But of course we can do it one by one, and that's why if we click on each structural element, we will have the option of only mesh the structural element. So if we go here, we will mesh both of them. How to interconnect two structural elements? If we want to obtain a congruent mesh, what are the options to interconnected mesh between the nodes which are in common of structural elements which are adjacent? We can check that in a new example. If you had performed the example of the shell buckling, you have, this is a very easy geometry. There are 3 rectangles. We just had defined my 3 areas using points. We can define it just three areas, but I think in the example, points were defined, then lines, and then surfaces between polylines. But here we have defined three structural elements for each flange and the web, IPE 100, so it has its dimensions. You see different thicknesses, and the important thing is, well, we have defined our material, and for each structural element we can perform the mesh independently. Okay, we can first set an edge size. In this case it's 1 centimeter of mesh, but we can do it, and we can mesh my bottom flange, which will be this one. But if we want to set the same controls for three of them, as they are homogeneous structural elements, we can select all three and apply mesh controls for all of them. 1 centimeter a size for three of them, and then mesh. As I have the three of them selected, I can mesh the three structural elements, and that's the same as clicking here the global mesh. And here I have my three. Change the view, or I can change the color if you want. Maybe it's better to see in green. Here I have it. I have another type of view, which is conical if you want as well. We have utilities for a view. In the view util, we have, well, in this case it's easy, but if you have a complex structure, this might help you. Okay, you have different planes predefined, but of course you can define your own clipping plane. Now here we can always check the number of elements total, and the particular ones are in each structural element. Okay, you can set this a different color. As we set the same size, we have a similar mesh between them, so we can merge nodes. How we can see that the nodes are connected or not? We can, well, plot nodes, or maybe it's better to element without the enhanced mesh control, so without the view of the thickness, and check nodes. Here we have the node numbering, and we can check here, and we can check that in the connection we have duplicated nodes, unless we want them disconnected. So we have nodes for the web and different from the nodes of flanges. We can leave them disconnected, but if we solve just like this, it will give us some rigid body modes, so we have to connect them somehow using springs, or this is not the case, contacts, or using connections for couple degrees of freedom. Well, in this case we want to connect them, and we will merge all nodes. We can select two structural elements to be merged of nodes, all of them, or just a group of nodes. In this case we will merge all nodes. Here we just set the radius of the sphere, which of nodes closest to each one, so the ones below this tolerance will be merged. I want to set, if I set a big one, a big tolerance or a small tolerance, it can merge some nodes we don't want to be merged. Okay, and here we have, you see here, we have merged with a big tolerance, so you can see a very funny shape. So if you want to do it again, I want to just merge the nodes which are coincident in the same location, so I just merge nodes with a small tolerance, 1 millimeter. We can check here, check nodes utility. We'll check the nodes which are within a tolerance. Okay, and here we check that there are no nodes in contact. If we do it again, but now without the merging of nodes, we will see the difference. The nodes which are closer than this tolerance here, and we see here that the ones in red are the nodes, the duplicated nodes. Click here to remove this view, and we merge again all nodes with tolerance of 1 millimeter. So now we have here our mesh, a linear load. You have a special chapter for loading, but in this case it's a linear load applied here. Have to, each time you must redefine all the conditions that were applied to nodes. So in this case I had applied a boundary condition on nodes. I can select by picking, because I want to set a cantilever beam 1 by 1 by clicking and pressing the control key, or I can set a box, select all of this. As well, there are other options for selection, which are selecting by location. Okay, so we can set here the coordinates of our selection and to select with more accuracy. We can check our boundary conditions. It's fixed at one end, and here we can just check. Well, we have applied a load boundary condition, and I must create a load case, and I had added, and I solve. Check always my output and check results. So is this mesh accurate or not? Do I have to refine? How do we estimate the error? You can remesh. Usually you have to start with a coarser mesh and see results, for example displacements, or you can check stresses as well. Change the units and check results. Check the maximum or minimum of stress or maximum or minimum displacement, and you can check the difference of each result depending on the mesh. Once you get an asymptote, you will know that the finer the mesh, the change in inaccuracy is not so big, so that's the time to stop refining. A matter of experience. If we want to set a quadratic instead, each node, each structural element has linear ones. For shells are 4 nodes, but if you want to obtain one more node in the middle of each edge, you can select the quadratic. The accuracy of course will be much higher, the same for the number of nodes. So these are things that you have to take into account. In another chapter I will show you tools for meshing solid elements. We go back to our slides. We have seen how to mesh beam structural elements and shell structural elements. Of course it will take more time to mesh, but still easier than the most general case, which are the solids. All these elements can be meshed with solid elements. but it will take more time and the results will not be more accurate. You have to always consider your time, engineering, the time of the engineer and the time of the machine. Always, if you want to create a submodel or a detailed analysis, local backlink or yielding of some connections, of course, solid element will give you more precise results. We'll continue with meshing and other interesting tools in next class. Stay tuned always in the virtual classroom. We'll keep you posted and check forums and you can send an email for any question. Thank you.